Hello everyone. Today I will talk about the second part of the generative models. In my first lecture, I talked about the generative models that are estimating the density explicitly. So briefly I can show here the main generative models are divided into two main categories. One is the explicit density estimation models and the second one is the implicit density estimation models. So in my first lecture I talked about the explicit density estimation models. By explicit density estimation mean that there is only a single network which take the data as input and generate and learn the data distribution. Those include autoencoders, variational autoencoders, pixel RNN, pixel CNN. Uh, but today I will talk about the implicit density estimation models, which is based on generative adversarial network. The content of this lecture is based on uh, the comparison between explicit and implicit density estimation. Then I will talk about the generative models, like the definition of the generative adversarial network, and then I will talk about the training procedure of the generative adversarial network and the modified version of the generative adversarial network, that is called deep convolutional generative adversarial network. I will talk about some limitations of the generative adversarial network, and then some remedies such as energy based generative adversarial network, info gain, and application wise I will talk about some other variations of generative adversarial network, such as conditional generative adversarial network, coupled generative adversarial network, and Laplacian pyramid generative adversarial network. Let's talk about the differences between the explicit and implicit density estimation models. So suppose we have a data distribution which is shown by this uh, distribution, and this one is the one which initially the model is thinking about. So initially the weights are random, the weights and biases are the parameters of the network are random. So whenever we provide the input image to this network, it generates the distribution randomly. So suppose this is the initial distribution generated while using the random weights. It has mean 3 and variance 1, whereas the real distribution of the training data having mean -1 and variance of 2. So we want to learn the model so that both the distribution are uh, uh, exactly or somewhat similar to each other. So when we start training, this distribution will uh, go towards distribution. So here we can see that now both the distribution show some similarity towards each other after training. So here now the variance of this distribution is 1.5 and mean is 1. From 3 it is converged to 1, and with more training, here we can see that both the distribution are lying on each other. So this is the explicit density estimation. We provide the input data distribution and we train the neural network to estimate the distribution of the input training data. However, in terms of the implicit density estimation models, um, there are actually two models that are fighting against each other to learn the exact data distribution. So here we can see again that this is the data distribution, the training data distribution, and this one is the initial data distribution that is generated by the model using the random weights. Now here we can see that this is another model which has high confidence here, that this portion belong to this distribution and this portion belong to this distribution. So it is we can see it from this curve. So the here the model has high confidence that both the distributions are different from each other. So what we need to do, we want to lose its confidence, the confidence of this model, so that it is unable to differentiate or distinguish between two distribution, the model generated distribution and the real distribution. So when we start training, when we are penalizing the confidence of that model, so here we can see that confidence is high, zero point 0.4 here, but after training here the confidence is dropped to 0.25. And now we can see that here in even in this space the model has very low confidence, but when we start training it with multiple iterations, this model then loses its confidence, and both the distribution, the input distribution and the model generated distributions are exactly matched here. And this is the confidence of the model as shown in this figure, which is almost zero. So now this model is unable to distinguish the real data distribution and the generated data distribution. Here what we did, we are penalizing the confidence of a model, and whereas the other model is trying to learn the data distribution. So when that model is starting learning better, it will penalize, or it will dominate the other model, and its confidence will start decreasing. And in this way we can learn the data distribution by using two different models. Generative adversarial network, in short, can be written as GANs. It is an acronym for Generative Adversarial Network, where each part has its own meaning. The generative part refers to the fact that GAN, or generative adversarial network, are generative. They are generating the data, they are generating the new samples, because it is learning the data distribution, so it has the capability of generating new images. So the generative part refers to the fact that the GANs are generative models. The adversarial part refers to the fact that the learning of the generative adversarial network is learned in an adversarial manner. Like there are two models and both the models are fighting against each other, and in this way we learn the data distribution. The network part, in this GAN is the GAN family is basically belong to the deep neural networks. Previously I talked about the differences between the generative and discriminative models, so let's revise it again here. The discriminative model actually take the input image X and predict the label, or we can say that the discriminative model learn the conditional distribution. It generate the label Y given the image X. uh, the discriminative model does not, or it cannot learn the data distribution. So if it cannot learn the data distribution, we can say that it lacks in generating new images. On the other hand, the generative model learn the data distribution P of X, and it has the capability of generating new images. Before going to the details of the generative adversarial network, let's see what GAN, or generative adversarial network, can do. Here are two images on the left side and on the right side. Can we see that which one is real image and which one is the generated image? So visually we cannot differentiate between these two images. What I mean to say is GAN has the capability of generating very realistic images. Similarly, application wise, it can do many tasks. So this I just selected one or two examples, but this is also one interesting example. It has application in graphics design, and it help the graphic designers. uh, so if we draw a stroke here, this is the green stroke, it will generate the image corresponding to this stroke. So this stroke, we are going to draw this stroke, and it will generate the corresponding image of that stroke. So here we can see the different variations of this stroke are generated here in terms of the complete images. Similarly, here we can see we drew this one stroke, and this is mountain shape. So the GAN generated the image with mountains, different variation of the mountains and the valley. Here we extend this drawing by adding one more stroke of blue color here, and the GAN generated the sky in each image. Here we can see, so it has many interesting application. You can go and find many different interesting application of generative adversarial networks. In generative adversarial networks, actually we are using the adversarial laws. The adversarial laws in itself is very powerful. So if we want to use the adversarial laws, so here suppose this is the ground truth sample, and if we use the mean square error loss as the objective function, we get this output image. So here we can see that the generated image is blurry, but if we use the adversarial loss, here we can see that the sharper image as compared to the MSC objective is generated here. So adversarial loss has its own importance. It generates realistic and very sharp images. This is another example where I picked this from this paper. So the goal here is to upscale this image. So a low resolution image is given, and different techniques are used to upscale this image. So this is the original image, and we downsample this image first, and then use different techniques how they can uh, uh, make, or how it can upscale this image again. So this is the bicubic uh, interpolation. This is the final output using this bicubic interpolation. This is the another neural network architecture which generated this one more realistic and sharper than this image. But here we can see that the GAN image, the GAN network generated the image which is more close to the real original image. So GAN has the capability of generating more realistic image by using its own adversarial laws or adversarial object. Now we will talk about the training procedure of the generative adversarial network. The generative adversarial network consists of two networks. One is the discriminator network. The goal of the discriminative network is to generate the samples, and we call those samples as the fake samples. The discriminative or the discriminator network, on the other hand, try to distinguish between the real image and the generated image by the generator. Or we can say that the real image or the fake images. Now in training, they are fighting against each other. We are training them against each other, where the generator try to make the realistic images to fool discriminator, so that discriminator is not able to discriminate between the real and the fake images. The discriminator, on the other hand, try to discriminate or classify the real images from the generated one or from the fake one. When we are training them against each other, at the end, the discriminator generate the images which are very realistic, and the discriminator feels difficulty in discriminating or classifying them into real or fake, because both the real and the real images are the ground truth images are same as the generated images. So in that case the discriminator cannot classify those images, and we can say that the generator is the winner. Once the generator is the winner, it will generate more realistic images. This is the generative adversarial network architecture. As I explained previously, that generative adversarial network consists of two networks. One is the discriminator part and the second one is the generator part. The discriminator part takes the samples which are generated by the generator, that we call G of Z, or it can take the real images from our data set. So this is the training data. The discriminator either pick the real image, and we pass this real image through this discriminator, and it says that whether it's a real image uh, or it is fake image if we give this as input. So the role of the discriminator is to classify between the real image and the fake image. The generator on the other hand take Z as input. Z is actually a random noise that is sampled from a Gaussian or uniform distribution, and this Z we call it latent space. Here we can see that we are not providing data as input to this generator. We are providing Z or the latent space as input to this generator, and the generator on the other hand generate images that we call G of Z, the fake images. Both the discriminator and the generator are differentiable because they are neural networks, and we have to train them by using the backpropagation algorithm that I already explained in my previous lecture, using by applying the adversarial laws here. So we minimize this objective here and train the parameters of the discriminator and the generator. Once it is trained, then this generator is capable of generating realistic images from this noise that is sampled from the Gaussian or uniform distribution, and at the end this discriminator will not be able to discriminate between the real or the generated samples, because this generator is producing or generating very realistic images. Now how we are training them? First, what we are doing, we are going to train the discriminator part. So we are training them in parallel, but the first step is that a discriminator take the real images. These are the real images from the given data set here. We provide it to this discriminator, and the corresponding label is provided here that this is the real image, and we are training this network. Similarly, we provide the noise as input to the generator part, and the generator is using those initial random weights to generate the images. So these are the images initially generated by the generator. We provide it to the discriminator, and the discriminator and its corresponding label is given here that these are fake. These are the generated images. So the what discriminator does, it discriminate between the real images and the fake images, and this is the objective function. We minimize this objective function and use the backpropagation algorithm to train the parameter of this network, and at the same time we are not training the parameters of the generator in this pass. In the next step, what we are doing, we are keeping the parameters of this discriminator fixed, and we use the same objective here and minimize this objective while using the parameters of this generator. So in this step, the generator will try to generate realistic samples. Now let's formulate the objective function or the loss function for the generative adversarial network. Um, as I already explained that there are two models which are trying to fight against each other, where we are minimizing the objective for one network and maximizing the same objective for another model. So this is kind of many max game, where we are trying to minimize one whereas maximizing another one. So this is the short representation of our objective, where we are minimizing the parameters of the generator while using this objective function, and maximizing the parameters of the and maximizing this objective while training the parameter of the discriminator. So this objective function is represented by this equation, where we can see that first the discriminator take the real image. X is actually the real image, and we are maximizing this. So if the input is given as the real image, we have to maximize it, or we have to make it to 1. Similarly, the generator is taking Z as input. It generates the image, and once it generates the image, we give it to the discriminator D, and the discriminator then classify it 0. So we have to maximize this 0. That's why we are putting 1 minus dg of z. So we want to maximize this. If it is 0, then this part will be maximized. So this is the expectation over all the samples that are passed through the discriminator. We maximize this part. Similarly, expectation of all the samples that are generated by the generator, and we have to find an equilibrium so that the generator generate the realistic images, and the discriminator is not capable of discriminating between the real and the fake images. This is the whole algorithm for training the parameter of the generator and the discriminator. So this part of the algorithm is for the discriminator, where we start from the training iteration, and then we perform some steps. We sample the latent space, such as z1 up to zm, from some prior distribution Pg of z, which may be Gaussian or it may be uniform distribution. Similarly, we sample or we take m examples from the data distribution. We provide it to the discriminator, where xi is the real example and g of z is the fake example or the generated example, and we train the parameter of the discriminator by maximizing this objective function in each iteration. So this is the learning algorithm for the discriminator. Now, to learn the parameters of the generator, we sample the m nice samples, such as z1 to zm, from the prior distribution Pg of z, and then we use this objective function here, and we want to minimize this objective function. So here we can see that dg of z, the discriminator is trying to discriminate between the real and the fake images. So if the generator generate the label which is close to 1, then the discriminator will feel difficulty in discriminating between the real and the fake examples. So here, suppose if it is 1, then 1 minus 1 is 0. Then we are not maximizing it now, because the generator is generating the images for which the label is close to 1. So here we are we want the generator to generate the images which are realistic. If it is realistic, it will give the label as 1, and then uh, at that time, at that point, the discriminator will not be able to discriminate between the real and the fake images. If the generated image g of z, if it is provided to the discriminator, it will give the label which is close to 1 if it is realistic, if the generator is well trained. And then at that point, the discriminator will fail to discriminate it between the real and fake images. The initial vanilla generative adversarial network was composed of only fully connected layers which take noise as input, and then the generator use this noise and generate images, whereas the discriminator was taking the real and fake images and was trying to discriminate them or classify them. So the vanilla generative adversarial network is capable of generating very realistic simple images. So these are the images which are taken from the MNIST dataset. MNIST is the handwritten digit dataset that consists of digits from 0 to 9. So here we can see that the vanilla again is capable of generating realistic handwritten digits from the noise distribution. However, when the vanilla GAN was used for the natural images, these are the CFAR10 dataset, which consist of the real images, real natural images of different objects. So when the GAN was trained on the CFAR10 dataset, it was not able to generate good quality images. So this is the kind of limitation of the generative adversarial network. But however, when it was trained on the face images, this is the CELIP A dataset, which consists of almost 200,000 face images. So when the vanilla GAN was trained on the face images, it was capable of generating the face images. So actually the face images are almost similar in structure. So it was capable to generate the face images. However, it could not generate the real images of different objects such as the CFAR10 dataset. Uh, so considering that limitation, in another paper that is mentioned here, they converted the vanilla GAN into a convolutional GAN. So what they did, they replaced the uh, fully connected layer with the convolutional layer, and they use the frictional strided convolution, and also they use the Bayes normalization layer inside the network. And for activation, they use ReLU activation in the hidden layer and hyperbolic tangent in the output layer. So this is the architecture of the DC GAN, Deep Convolutional Generative Adversarial Network, where a latent space Z of 100 dimension is given to this network, and the hidden layers are the convolutional layers, whereas the output layer is the layer which is of the same size as the required image. Now once the uh, deep convolutional generative adversarial network uh, was trained on the natural images, uh, it was able to generate very realistic uh, output images. So actually there is reason behind this. The fully connected layer uh, are sharing the parameter across the whole image, so that's why it ignore the small features in the image, whereas the convolutional layer, the convolutional architecture pick each feature and code them, and then we can even generate the fine details in the image using the convolutional structure. Uh, in their paper, they also did some interesting things. Like what they did, they, find the latent space for the samples for the person with eyeglasses, uh, and that sample is corresponding to male. Similarly, they also found the latent space of the man without glasses. When they subtracted the latent space of the man with glasses from the latent space of the man without eyeglasses, and then they found the latent space of the woman and add this residual with the latent space of the woman without eyeglasses, and when they pass it through the generator generated very interesting results with the woman with glasses. So this was just one interesting application, like uh, uh, it says that the latent vector is coding some interesting information, because this the learning of this generative adversarial network is it estimates the data distribution. The data distribution is actually it fit all the training example in the Gaussian or the uniform distribution, and we can generate many interesting results while using that distribution. We have many different kinds of generative models that I explained in my previous lecture, such as variational autoencoder, pixel CNN, pixel RNN, and Boltzmann machine. Like in variational autoencoder, we were detaching the decoder part, and then sampling the latent vector and providing that latent vector to the decoder and generate the images. So if we have all those generative models, then what is the purpose of the GAN network? Then why we need the generative adversarial network? So let's see what are the advantages of the generative adversarial network. Actually, the sampling procedure in generative adversarial network is very simple. Like we have a uniform distribution or we have Gaussian distribution. All we need to do is just sample the latent vector from that distribution. Secondly, like in variational autoencoder, we were using the maximum likelihood estimation, and sometimes it is not tractable. Uh, so, in term of the generative adversarial network, the training is very easy because this is the direct training. It does not involve maximum likelihood estimation. Third, like the generator is not taking image as input. Like in variational autoencoder and all other autoencoder, the input were at that time the input were images, but here the generator take the noise as input, which is sampled from the data distribution, and then generate the images. So the generator is not seeing any kind of training sample. We can say that the generator uh, here in the generative adversarial network is more generalized, or the training is more generalized. Similarly, in terms of the variational autoencoder or other model, it was not able to learn the different modes in the data distribution. But the generative adversarial network has the capability to learn the multi-mode problems. In explicit density estimation model, computing the data distribution is not straightforward, whereas the in generative adversarial network, uh, estimating the data distribution is simple, and it can generate the images from the noise easily. But there are some limitations of the generative adversarial network also. One is it has the gradient vanishing problem. Like when the gradient is close to zero, then the training stops and it does not learn properly. Secondly, non-convergence. And the third one is the mode collapse. So I will talk about these three problems briefly in my coming slides. Now let's talk about the gradient vanishing problem in vanilla generative adversarial network. Here we can see that this is the objective function for training the discriminator part. Similarly, this is the objective function for training the generator part. The discriminator actually take the real image and classify it as 1, and it take the generated image or the fake image and classify it as 0. So when the discriminator is very confident, and when we provide the generated image to the discriminator, if it classify it as 0, then we can see here, if we put 0 here, then log of 1 minus 0 become log of 1, and log of 1 is 0. When this is 0 and the gradient of 0 is 0, then we once the gradient is 0, then we cannot propagate back the error. So this stop the learning of the generator. So this is one main issue in the generator, the gradient vanishing problem, when the discriminator is quite confident of the input. The second problem of generative adversarial network is related to the convergence. So the using the gradient descent for learning the generative adversarial network has its own limitations. Actually, in simple deep neural network, what we are going to do, we are minimize the objective function by providing the input. This is the simple loss we are going to optimize in terms of this explicit density estimation models. But the generative adversarial network consists of two players, two models that are training against each other. In one architecture, in one network, we are maximizing the objective, and in the next network we are minimizing this objective. So here we can see that we are minimizing this objective uh, for the generator, and we are maximizing this objective for the discriminator. So there are two contradictory kind of optimization, and when we are when we are using the stochastic gradient descent to optimize this objective, it will not converge to its optimal solution. Actually, gradient descent is basically uh, successful in terms of the convex optimization problem if it is unidirectional, but this is kind of two directional. One, in one direction we want to minimize it, and the second direction we want to maximize it. So there is kind of fluctuation. So let's explain this non-convergence issue by taking an example. For example, we have a function and we have two networks. So the first network, or the one player, update the value of x to minimize this f1 of x, which is equal to xy. Similarly, the second network, or the second player, update the parameter y and x are the variables here. We want to find the optimal point for this function. So the second network update the variable y to minimize this f2 of y. So here we are minimizing this function because we put negative sign here. So rather than maximizing xy, we put negative sign to minimize it. So it is alternative way of maximization. So what we are going to do, we want to take the gradient and then back propagate the error and update the value of y. So first what we are going to do, we are taking the derivative of this function with respect to x, because x is the variable here. So when we take the derivative of f1 with respect to x, it becomes y. Similarly, in the second network, we are going to optimize this function by changing the value of y. So we need to take the derivative of this f2 of y with respect to y, and it is minus x. Next, we need to change the value of x and y. We need to find the new value of x by using the gradient descent approach. So x is equal to x new is equal to x old minus learning rate into this change. So this is basically change here. We are adding up this here. Similarly, to find the value of y, to optimize f2 of y, we just the new value of y is equal to old value of y plus the learning rate into this value. So actually this is minus sign, but minus with this minus x becomes plus, so plus learning rate into x. And because of this opposite sign, with every gradient step their oscillation increases like this way. So initially it is small, but as the gradient is in the opposite sign, so with the passage of time it is increasing, and it does not uh, converge to its optimal solution. The next problem is the mode collapse problem. What is actually mode collapse? Uh, like when we are learning the generator tries to learn the overall data set, different variation in the data set, but in term of the mode collapse problem, the generator only learns specific samples and it ignore other samples. Like suppose this is the target distribution and we want to learn this target distribution. uh, so in term of the iteration, in zero iteration it is like this. These are the expected results. After 5k iteration it look like this. The generator is able to generate this distribution like this. After 10k iteration the generator is able to generate this distribution like this. After 15k iterations, if it is successful, if the training is successful, the generator will generate this distribution like this. After 20k like this, and after 15k like this. So here we can see that the generator is successful in terms of generating this distribution, but this is not always the case. Sometimes the generator is like in zero iteration it generate this way. After 5k iteration it generate a distribution like this, and after 10k now it is focusing on specific mode. It is not learning the whole distribution, it is just focusing on specific distribution in each iteration. In the after 15k iteration it is learning this mode, similarly this way. So here we can see that the generator fails to generate the uh, proper distribution. It cannot explore all the modes, so this is called the mode collapse problem. uh, let's take a real example. When we are training the generator, we are sampling the latent space from the noise distribution, and in terms of the mode collapse problem, the generator will always generate similar kind of output images. So here we can see that if we sample different value of z, it is generating the output. If like suppose here we have sampled z values 3 times, so first time it generated this main kind of this skating. uh, I don't know, it's actually kind of mixture, like it's not very clear like what is the generator want to generate. um, so second time when we sample the z value, even though it's randomly we are sampling it, it still generate similar kind of image to the previous one. So here we can see that all the images are generated exactly similar to each other. Similarly, this is the uh, another example. So this is actually the mode collapse problem. uh, Whenever even though we are changing the z value, even though we are changing the latent space, but the generator is not able to generate the different images, because it's stuck on specific modes or specific images. Many attempts have been made by the research community to solve this mode collapse problem in vanilla GAN. The first attempt is called unrolled GAN. So in unrolled GAN, the authors just train the discriminator multiple times with just single step of generator training. So first what they did, suppose they train the discriminator 5 times and then train the generator once, so that
the discriminator learn more than the generator, and it will focus on the diversity. So they give more weight to the training of the discriminator rather than the generator. This was the first attempt that they call it uh, unrolled gain. The second one is called Wasserstein gain. This Here they modified the objective function. So here, like the discriminator take the real image is x and give the output. Similarly, the discriminator also take the fake image. So D is for discriminator, take the fake image that we call G of Z. And what they did, they modified the training objective of the uh, vanilla gain by minimizing this cost function uh, whole square. This is the mean square error between the generated output of the discriminator from the real image as well as from the fake image. So this is called the Wasserstein gain. There are other attempts such as many batch gain and supervision with label. So let's talk about them in the coming slides. First, I will talk about the many batch gain architecture. So, in terms of the mode collapse problem, the generator actually produces very good samples, but not all, few of them, and the rest, like the generator only produce few good results, and it lacks the diversity. So once the generator start producing realistic images, then the discriminator cannot distinguish the real images from the fake one. So the discriminator is easily fooled. So to address this problem, the discriminator should know between the different images. Like it should know between the real and the fake images, so that the generator learn the diversity. So what is the solution? The solution is like, how about if the discriminator, like the previous training is based on image wise, we give the single image to the discriminator, and the discriminator classify it either real or fake. But how about if instead of giving single image, if the discriminator look at the whole mini batch of images, if there is lack of diversity, like in term of the mode collapsed, there is no diversity because all the outputs are exactly the same, so there is no diversity. uh, so if the discriminator get the inputs which lack the diversity, then we can decide that this is a mode collapse problem, and we need to force the generator to generate more diverse samples.
Now, to solve the mode collapse problem in vanilla generative adversarial network, the mini batch generative adversarial network extract the features that capture the diversity in the mini batch. So, what we are going to do, rather than passing each sample to the discriminator, we pass a group of samples to the discriminator that we call as mini batch, and then calculate the L2 distance between all the features inside that mini batch. Once we calculate the L2 distance, we concatenate the, the difference with the original image and then provide it to the discriminator. So once we calculate the L2 difference, if the difference is small, it means that there is mode collapse problem and the discriminator can easily classify it as fake. But if the diversity is more, it means that there is no mode collapse problem. So when we concatenate that difference with the input image, uh, it then provide the diversity, and the discriminator can guide the generator to generate more diverse images rather than a single or one or two good samples. The second one is the supervision with label approach that is going to solve the mode collapse problem. What we are going to do here is in traditional GAN, the discriminator only classify the real from the fake, but using this supervision with label, we are also uh, classifying it real and fake along with its category. So rather than just a binary problem, we are making it multi output problem. Like there is label for car along with fake. Similarly, dog along with fake are real. So we are just associating its corresponding label, and then uh, once we associate the label, then the mode collapse problem is solved, because the label is all the time changing. Even if the generator is producing a single image, but the label is different, so the discriminator will force the generator to generate realistic and required output, and in this way the mode collapse problem is solved. Similarly, to solve the gradient vanishing problem, this paper tried to uh, modify the objective of the vanilla gain. So this is the objective for the vanilla gain, where we are going to maximizing this objective for the discriminator training and minimizing this objective for the generator training. In this objective, for the real images, the discriminator should give output as 1, whereas for fake images, the discriminator should give output as 0. So here what they did, they just reverse this binary classification label problem. uh, in this case, the discriminator will generate 0 if it get input as real image, and it will generate 1 if it take the fake as input. So it actually, what they did, they just reverse the problem, the objective of this generative adversarial network. Once we decide that the discriminator will generate the output as 0 if it uh, take input is real image, and it will give the output as 1 if the input is the fake sample. So this is the objective for the discriminator. We want to maximize this. The output of the discriminator is probability, and the maximum value of the probability is 1 and minimum is 0. So to maximize this, uh, as this is equal to 0 for the real image, so to maximize this, we are subtracting this from 1. Similarly, this is 1 for the fake sample. Here we can write this in term of the minimization problem. We are changing this maximization problem to the minimization problem. uh, so here we can see that d of x is 0, so we want to minimize this. We want this discriminator to give 0 for the real image. Similarly, we want this generator to give 1 for the fake image. So we are minimizing this, that's why we are subtracting this output. If it is 1, it should be how it will be minimum if we subtract this from 1. How can we make this as 0? By subtracting it from 1, it will become 0. So we are going to minimize this objective. Now once we change this problem into a minimization problem, we can replace this cross entropy loss function with any other loss function, and we can define some value m rather than a single value, rather than a single binary value 1 or 0. We can set some values and then uh, optimize this objective function. So it will give high values for fake samples and low values for real samples. The authors of this paper call this modified version of the vanilla generative adversarial network is energy-based GAN. So this is the architecture of the vanilla uh, GAN, and this is the architecture for the energy-based uh, generative adversarial network. So in this modified architecture, the generator tried to generate samples with low values. Actually, the generator want to generate the realistic output, and the realistic or the real images has label 0. So the generator will try to generate samples which can generate the 0 output in terms of the discriminator. And what will the discriminator try? The discriminator will try to assign high values to the images that are generated by the generator. So here we can see that the modified energy based gain is shown here, and here they replaced the discriminator uh, with an autoencoder. So for discriminator, they are going to uh, increase this loss function. Uh, this is the mean square error between the generated output and the input to the discriminator. Here the output of the discriminator is not single value but the image, because we are using autoencoder. And similarly, it should give low reconstruction error from the for the real sample for training the discriminator. Um, After using this these changes to the vanilla again, we can see that the energy based gain can generate realistic images. It can avoid even the mode collapse problem and the gradient vanishing problem, and these are the results of the energy based gain on different real natural images. Uh, there are some failure results on the face images. So here we can see that some of the images are not well generated using this energy based gain. Now there is one important application of the generative adversarial network. Like suppose we say that there is a latent space, and we are sampling that latent space and give it to the generator, and the generator will generate different images. But how about if we change one dimension of that latent space and then give it to the generator? What will be the behavior of the generator? So uh, we want to analyze the importance of this latent space in terms of generating different images. So we can explore this latent space. How? Like we will fix the rest of the dimensions of the latent space and just change one, and then see what is this first dimension correspond to. Like suppose these are the face images, uh, and if the first dimension in the latent space suppose show the pose of these faces, and the second dimension suppose correspond to the elevation as shown here. The third dimension is related to the lightning condition in the input images, and the fourth dimension suppose is related to the wide or narrow angle. So we want to explore this problem. Similarly, this is second example. We want to find which dimension of the latent space is corresponding to the rotation, and which dimension of the latent space is correspond to the width of the chair. So previously we studied the DC gain architecture, where the authors just subtract the latent space of the men with eyeglasses from the latent space of the men without eyeglasses, and then added it with the uh, latent space of the woman, and the resultant was the woman with eyeglasses. But that architecture, that can learn these things by its own. There was nothing in the objective function to force these dimensions to specific features. So in this new paper that is called InfoGain, what they did, they embed these things in the objective function. So once they embed these things in the objective function, then the game can specifically learn those features. Like in this example, uh, the the generative adversarial network can learn the rotation with specific dimension of the latent space, and some other dimension of the latent space will learn the width of the chair, and there may be multiple features that we can dedicate, like what we need to learn in this input data. So to learn those unique variations in the input data, the authors of the InfoGain, they disentangle the the features in the input. Like what they did, actually normally the latent space Z, when we sample it from the uniform or the Gaussian distribution, it's kind of real representation. So, and there is no meaningful information for a specific feature. So what they did, they disentangled, they separated those information. How they separated it? First they sample the z vector from the Gaussian distribution or the uniform distribution, and secondly what they did, they concatenate the c vector. C vector actually contains the information of different things, like suppose this is the angle, or this is the thickness of that object, or this is the pose of that object. So what they did, they concatenate these two values. This one is related to the specific information, and this one is correspond to the whole image, and they calculate the this c vector by using the correlation factor. How they calculate this c vector, I will explain in the coming slide. So they use the concept of the mutual information. um, how we can describe the mutual information. Suppose there are two variables x and y, and how they are correlated, how much information, mutual information are there in between these two variables. It is represented by this formula. So in the info gain, what they did, they just added, they just subtracted this mutual information, they just include this mutual information uh, with the given objective, with the given classical objective of the GAN network. So we want to maximize this mutual information. This is the overall structure of the info gain. So what they did, uh, this is the normal z vector that is sampled from the Gaussian or the normal distribution. They can concatenate the c vector with this z latent space, and then give it to the generator. The generator then generate the image that is called fake image, and the discriminator either take the fake image to classify it to the fake, or it take the real image and classify it to the real image. Similarly, there is another network that is taking this g of z and generate c dash, and using that mutual information we are maximizing this objective. And once we maximize this, then this architecture has the capability to learn different meaningful features or information in the input image, such as pose, uh, and many different information. So after training the info gain with that specific objective, we can see that it is capable of generating some interesting results. So here we can see that this is the input image, and there are different poses of this face image. Similarly here, uh, now this one show the presence or absence of the eyeglasses. So here we can see that uh, the this is the one aspect of the input image. This is second. Here we can see that there are eyeglasses not fully visible. Here we can see that they are fully visible here. Similarly here we can see that the hair style is changed, so we can see that different hairstyles are here, and there are this one shows the emotion in the input image. So here we can see that there are different emotion, kind of sad to a happy face, or many different emotions. Now there is another type of generative adversarial network that is called conditional gain. So what is actually conditional gain? We are giving the generator input, and we are concatenating some class labels, like how we did in the info gain. We were giving the C vector, but that was not specific. We were learning that C vector. Here the condition is specific, like this is the class label. So suppose if we are giving 0 as input, so we will also concatenate this label, which is 1000. Similarly, if we are giving 1 as input, we will concatenate 0100. If we are giving 2 as input, we will concatenate 001 as along with this input image. So this is called conditional gain because it is condition on its class also. Uh, Here I will briefly show what is the difference between the vanilla gain and the conditional gain. So this architecture is for the simple vanilla gain, and this one is the conditional gain. So here we can see that this is the input, Z is the input, and this is the corresponding target uh, for this image, for this uh, for this Z input. We are giving both as input to the generator, and the generator generate this as output, uh, and we then concatenate that target with this image and give it to the discriminator. Or in term of the real image, we are giving the real image and concatenate the target with this and give it to the discriminator. So why we are doing this? There are actually many application of this conditional generative adversarial network. So this conditional generative adversarial network can be used for image to image translation. So suppose this is the input image, which is the kind of label of the this real image. It can translate this label to this image, or this image to its corresponding label. This is the aerial to map view. Similarly, this is label to facade, and this is the change between different colors, and here this is from sketch to real image, and this one is from night to day and day to night conversion. So how this image to image translation architecture works, uh, like suppose in, this is the discriminator part, which take both as real input. So here we can see that this is the label and this is the input image. This is the label and this is the input image, which is given to the discriminator, and the discriminator just generate the real or fake pair as output. Similarly, in term of the fake image, we first give this image as input to the generator will generate this as output, and we are conditioning it on the input image, which is given to the discriminator, and the discriminator has to classify it as a fake pair. So this architecture has the capability of translating images between different domains. It can translate images between day and night, between sketch and real images, and many other, as I discussed in the previous slide. There is another application of this conditional generative adversarial network. Like suppose we have text here, and once we give this text to the network, it can generate its corresponding image. So these are the different examples of the images generated from the given text. So how this network works, uh, this is the text. We just encode it and give it to this architecture. It generate, this is output, and similarly at the same time we sample z from the Gaussian distribution with zero mean and unit variance. We concatenate these two and give it to the generator, and the generator generate the uh, image as output that we are then giving to the discriminator, which discriminated into real or fake images. So this conditional GAN has the application of translating the text to the corresponding image. Similarly, it can also be used for face aging. Like this is suppose input image. First it is encoded into latent space z naught by using this encoder architecture, and then we can concatenate it with its corresponding label, give it to the generator, and the generator will generate image. Similarly, we are also preserving this uh, identity by using this objective here, and then we can concatenate these two to the second generator, and the second generator will generate the output images with different age. So this is another application of the conditional generative adversarial network. So these are some of the results from the face aging with conditional generative adversarial network. These are the input. This is the initial reconstruction, and after optimization we can see that these are some uh, images which looks if it is young it look old, and if it is old it look young. So these are the different age which is written over here. Like it can be go from up to 18 year, it is transformed to plus 60 female here. So it can perform the face aging also. There is another kind of game that we call the coupled game. The coupled game actually learn the giant distribution uh, between multiple domains. So suppose these are the images of different kinds. So we are using the coupled gain to learn the giant distribution between these two domains. This gain has this generative adversarial network has application in domain adaptation and image translation. Like it translate images from one domain to another domain. Like how this that conditional generative adversarial network works. This is the architecture of the coupled GAN. Like this is the first GAN network, and this is the second GAN network. So this is the Z which is sampled from the uniform distribution or the Gaussian distribution, and here we can see that the first initial layers are sharing the weight parameters, and then the rest of the layers are not sharing the parameters between each other. So this is G1 of Z from the first domain, G2 of Z is from the second domain, and there are two discriminators which are not sharing the parameter in the initial layer, but they are sharing the parameters in the output layers, and the discriminator then give the output as f1 g of z and f2 g of z. So this is the architecture for the coupled gain, and using the coupled gain we can see that it can transform the hair color from here to here. Similarly, it can also change the facial expression, and it can also add or remove the eyeglasses somehow. Here is one another important and is interesting variation of the generative adversarial network that we call Laplacian pyramid adversarial network. This architecture uh, is using the concatenation of many generators and discriminators, and it perform the upsampling. Like suppose we have a low resolution image, it can increase the resolution of uh, the, that low resolution image and give us a high quality output image. So here we can see that the first generator takes C3 as input and it generates I of 3, and here we upsample this I of 3 to I of 2 and then give it as input to the second generator along with the sample Z2 from the Gaussian or the uniform distribution. This G2 will then generate H2, and we are adding I2 and H2 here and then upsample it here again, uh, uh, add them here, and this is the output, and then upsample it here, give it to the G1 along with the input Z1 which give H1 tilde. We then add this with the previous L1, uh, and when we add them it give this I1, and then we upsample it again and give it to the G0, and similarly this is the final uh, image with high resolution. In this lecture uh, I covered the implicit generative model that is called generative adversarial network. I talked about the architecture of the generative adversarial network, the objective of the generative adversarial network, its limitations, how the researcher approached this problem, and I also discussed few applications of the generative adversarial network. We can find many more applications of the generative adversarial network. It is an active research area. We can go to the web and find many more about this topic, because we cannot cover this huge topic in just one class. So you can see and search the web, and there are many applications. So that's all from for today's lecture. Thank you for listening.